So today we will discuss theory of simple bending, right? We have discussed already the about the introduction of theory of simple bending in previous class. For now, we will discuss what is today we will discuss the derivation of theory of simple bending. Right. For that, we will consider a small length of simply supported beam subjected to a bending moment and consider two sections AB and CD which are normal to axis of NN. Right. For that, we have this section. We have this section, right, in which A is a transverse section and B is cross section of the beam. That is cross section of the beam, right. So in transverse section, that is A diagram, we have this beam A, B, C, and D, in which NN is neutral axis of that section, right? NN is neutral axis of that section, and here is cross section of this particular beam. This is the transverse section of the beam, and this is cross section of the beam. Okay. Suppose this BD length is dx, a small length dx. We have supposed a small uh, cross section of transverse section of the beam. Clear? Okay. So now we have considered two sections AB and CD which are normal to axis of NN, that is neutral axis. Due to action of bending moment, a small length dx will deform. When we will apply this bending to the beam, the fiber of upper side to the neutral axis will shorter, and fiber to the lower side of the neutral axis will get into the tension. Will get into the tension. And layer of beam which were originally of same length do not remain of the same length. Right. So top layer above NN deformed from AC to AC dash, that is AC, right, and it will deform to AC dash, right. This A point and this A point deformed to the A dash, and this C point deformed to the C dash. So upper fiber will be compressing, right. Upper fiber will be compressing somehow, and right now we can see this B fiber is B dash and D is D dash. So we can easily conclude from this that BD length is smaller than B dash D dash, right. That's why we can say that BD fiber, that is lowermost fiber of the beam, is getting into the tension and it is expanded, right. So lower fiber to the neutral axis are expanding and upper fiber to the neutral axis are getting compressed after the application of load, right. Okay. uh, the line of intersection of neutral layer on a cross section or with transverse section of the beam is known as neutral axis. This NN, that is getting to the uh, intersection or to the principal centroidal axis from this of this beam is said as neutral axis, that is line of intersection of neutral layer on a cross section. Now we can easily conclude the top layer has been shortened maximum and the lower layer has been expanded maximum. So there is maximum compression at upper side of the neutral axis at the topmost fiber, and the this lowermost fiber will have maximum tension. This theory is called as simple bending. We already have discussed in previous class the assumption of the theory of bending. We are repeating this in today's class. That material of beam is perfectly homogeneous, same material throughout, and isotropic, right? That we have discussed in the previous class. The beam material is stressed within its elastic limit and thus obeys Hooke's law, right? And it will obey Hooke's law. The value of Young's modulus E, we can say that it is same in tension and compression. The transverse section, which were plane before bending, remain plane after bending. That is our most important assumption of theory of simple bending. We have this assumption in every subject related to the engineering mechanics, related to the physics, related to the strength of material. And we will, when we will move further to the structural analysis, that assumption will never get changed. The transverse section, which were plane before bending, remain plane after bending also. So that entire beam cross section is assumed to rotate about the neutral axis, right? This is neutral axis, and this entire cross section or intersection will rotate with respect to this neutral axis. Okay. Now, fifth assumption is each layer of beam is free to expand or contract independently of layer above or below it. For that, we can see this diagram. This is neutral axis, and that are the above fibers and that are the lower fiber of this beam. With all of the fibers are independent. They can expand it or can be shortened throughout the cross section of the beam. Right. The sixth assumption is the radius of curvature of the beam is very large in comparison to cross-sectional dimension of the beam. Right. The beam is initially straight and all longitudinal filaments bend into circular arc with a common center of curvature. Like who is this? Okay. Now we will move further for the derivation of bending equation and bending stress. For this, consider a portion of uniform beam subjected to pure bending due to action of bending. The part of length bx will be deformed. Right? We have this beam ABCD, that is the uppermost fiber is contracted into A dash C dash, and lowermost fiber BD is expanded to the B dash D dash. Let R is equal to radius of curvature of beam or radius of neutral layer N dash and theta is equal to angle subtended by A dash B dash and C dash D dash. We can see this in this diagram, right? We have this after bending diagram A dash C dash and B dash D dash, that is neutral axis N dash that were before NN, and after bending it will become as N dash and EF is a smaller part of the transverse section. That fiber will become E dash Y dash, and this is at distance Y from the neutral axis and N. Right, that is angle theta subtended by A dash B dash and C dash D dash. Right, it is meeting at point O, that is center of this curvature. Now we will consider a layer EF at a distance of y below the neutral layer NN. After the bending, this layer will be elongated to E dash F dash. Right. This is EF fiber. We have considered this, and this is at y distance from this neutral axis. After bending, it is at the same distance from the neutral axis, right? But because it is curved, the EF will become E dash F dash, right? Now E dash F dash is equal to NN is equal to TA, where EF is equal to original layer and NN is equal to the length of neutral axis, from where we can easily after bending, we can easily conclude that N dash will remain unchanged. Why? Because we have discussed the plane section will remain plane before bending and after bending. But length of layer E dash F dash will increase because it is below to the neutral axis, right? The uppermost fibers, the upper fiber of the neutral axis will decrease by the length, and lower fiber of the neutral axis by the neutral axis will get expanded, and length of these fibers will be increased. And EF dash, E dash F dash is below the neutral axis. That's why the length of layer E dash F dash will increase. NN is equal to N dash is equal to dx, right? NN is equal to N dash, or NN have length dx, right? For O N dash, right? That is O N dash. This is, suppose this is the arc O N dash. Let me draw this. That is your point O. That is N dash and N dash. We have separated this part from the this diagram. O N dash, right? So O N dash will have, this is N dash is arch, right? And this is angle theta, right? Who have drawn that, whoever is this, right? O N dash is equal to, angle is equal to arc divided by radius, right? Arc is equal to angle multiplied by radius. So theta will be equal to N dash upon R from here, and after that N dash will equal to R theta. Clear? And we know N dash is equal to dx by what? Plane section will remain plane. The plane section that was plane before bending will remain plane after bending. We will have this, and NN is equal to N dash is equal to dx, right? Okay. So from here, N dash is equal to R theta and dx is equal to R theta, and that dx is also equal to EF, right? Then EF is equal to R theta. Now we will have to draw one more arch, that is O E dash F dash. Taking this arch O E dash F dash, right? O E dash F dash, right? So right now we have this arch, that is point O, that is E dash, that is F dash, right? That is angle again theta, right? So now we will have from this diagram, angle is equal to arc divided by radius, theta is equal to E dash F dash, that is arch. E dash F dash is a arch, it's a curvature, right? E dash F dash divided by R plus Y. Radius is now R plus Y. right? Radius is now what? This O E dash, this O E dash will become what? This O E dash having length. This is the radius of that particular arc, right? So it will become what? R plus Y, right? R plus Y, right? So now we will have this as E dash F dash upon R plus Y. Finally, we will have E dash F dash is equal to R plus Y dot theta. So now increase in length of the layer will have we will have EF is equal to E dash F dash minus EF, right? That is finally R plus Y multiplied by theta minus R theta. E dash F dash is R plus Y dot theta, and EF is equal to R theta that we have taken from there. Finally, it will have Y dot theta. We will have this increase in length is equal to Y dot theta. So we know what is strain. Strain is strain क्या होता है? Strain is increase in length divided by original length, या change in length divided by original length. In this particular case, we have increase in length, so that's why we have written that this is increase in length. This is increase in length, right? This is increase in length divided by original length. So finally, we will have y theta upon r theta. So we have E is equal to y divided by r. That E is epsilon E. That is strain. So strain is change in length upon original length. Change in length is y theta, and original length is r theta. After that, we will have strain in layer EF as y upon r. And we know Young's modulus is stress upon strain. So we will have this sigma is equal to E multiplied by strain, and we will have the value of strain as E is equal to y upon r. Putting it in here, we will have finally E sigma is equal to E multiplied by y upon r. From here, we can easily write that sigma upon y sigma upon y sigma upon y is equal to what? Is equal to E upon r. This is the first phase of deriving the theory of simple bending. We have halfway already. Now we have to derive the second part of this derivation, that is moment of resistance, right? Moving further, we will have to first discuss this sigma E upon r is equal to sigma upon y. We will have to first discuss about the neutral axis, right? Okay, now we are again with this diagram. We have this diagram. This is the rectangular section of the beam having a layer of small length dy at y distance from the neutral axis. This is the stress diagram of this particular beam having rectangular cross section. Let us read first. If a section of beam is subjected to pure sagging moment, then the stress will be compressive at point above the neutral axis and tensile below the neutral axis. How we will draw this diagram? Let us see. Like we have already discussed this, that in rectangular section, the upper fiber from neutral axis will be in compression and lower fiber in neutral axis below the neutral axis, lower fiber below the neutral axis will have tension, right? So for that, we can easily draw the compression diagram. That will be like this. This is, if this is neutral axis, suppose upper fiber will have this much compression and lower fiber will also have this much tension, then this will become like that. That will be the sigma C, that is compressive stress, and sigma T, that will be the tensile stress, right? Okay, tensile stress will be at below the neutral axis. Stress at a distance y of neutral axis, sigma is equal to y multiplied by E upon R, that we have derived from the above derivation. Okay. Finally, we will have this. Let neutral axis is n is neutral axis, then let dA is equal to that area that is having length that is having width dy and length as dx, right? So dA is equal to area of the layer. Now force on this layer will be stress on the layer multiplied by area of layer, from where it can be written sigma is equal to P upon A, right? We were having sigma is equal to P upon A. P is force. So from here we will have P is equal to sigma multiplied by area, right? So stress on the layer is y multiplied by E upon R, and area is, that small area is dA, right? So we will have y multiplied by E upon R multiplied by dA, that is force in this layer only. For force in the complete layer, in the complete section, what we will have to do? We will have to integrate this in respect of this limit, right? So total force on beam will be equal to integration of y multiplied by E upon R multiplied by dA. Now we know for pure bending, as we have discussed in our previous class, that for pure bending there is no force on the section of the beam, right? There is no force on the section of the beam. Clear? Right? So if there is no force on the section of beam, then force will be equal to finally 0. So making it to the 0, E upon R integration y multiplied by dA will equal to 0. From here, integration of y multiplied by dA is equal to 0. It represents that moments of area dA about neutral axis, right? Y multiplied by dA is, as we know, is what? It is what? Y multiplied by dA. Y multiplied by dA is what? It's a first moment of inertia, right? Right. It is a first moment of inertia. After that, it will become A y bar, right? After integrating it, we will have y multiplied by dA is equal to A y bar, right? Okay, so we can say if this is equal to 0, that means neutral axis will coincide with the centroidal axis. ये हमने इंजीनियरिंग मैकेनिक्स में पढ़ा है कि अगर हमारा फर्स्ट मोमेंट ऑफ इनर्शिया 0 के बराबर होता है, that means neutral axis will coincide with the centroidal axis, right? And centroidal axis of a section gives the position of neutral axis, right? So finally, we will move further for the moment of resistance. Don't worry, I will give you these notes, right? Finally, we will move further for the moment of resistance. Now, due to pure bending, the layers about the neutral axis are subjected to compressive stresses, right? And below the neutral axis are subjected to tensile stresses, as we have discussed in our previous topics. These stresses are from a couple, right? No force is occurring, so stresses are from the couple, and forces will act on these layers. Whose moment must be equal to the external moment, right? Okay. Now force on layer at a distance y from neutral axis will equal to y multiplied by E upon R multiplied by dA. Right? Force on this layer, force on the layer, that is at y distance, at y distance, this layer dy of area dA is at y distance from neutral axis. Now we will have this moment of the force about neutral axis is what? Force multiplied by perpendicular distance, right? Force on layer multiplied by perpendicular distance. What is the force on neutral axis? That is y multiplied by E upon R multiplied by dA, and multiply by y, that is perpendicular distance from neutral axis y. So finally we will have E upon R multiplied by y square dot dA, right? And it will be into the integration for the whole section of beam. If we are considering the whole section of the beam, we will have to integrate this. E upon R is constant, so it will remain outside of the integration. E upon R integration y square dot dA, right? Let M is external moment applied on this section. We will finally have M is equal to E upon R integration y square dot dA, and I is equal to y square multiplied by dA. We know that is second moment of area, or second moment of inertia. Actually, moment of inertia of an area is a misnomer. That is not happening in anywhere in the world. Moment of inertia will be of 3D body only, always. But for now, we will have second moment of area. That is M is equal to E upon R multiplied by I, right? From here, I is equal to this. So we will have M upon I is equal to E upon R. And we know E upon R is also equal to sigma upon Y, that we have discussed in our previous derivation. M upon I is equal to E upon R, and E upon R is previously equal to sigma upon Y. So finally we will have this bending equation, or Bernoulli-Euler equation we can say, that is M upon I is equal to sigma upon Y is equal to E upon R, right? This is our final bending equation, or we can say Bernoulli-Euler equation. We will discuss the next part of theory of simple bending, that is introduction to bending stresses and shear stresses distribution, in our next class. For today, we will end with this, but I will take your queries, right? Your queries, right? Okay.